Hello class, welcome to this video on chapter 5 review. We broke it down by lesson 5.1, 5.2, 5.3. So we're going to start with the 5.1 questions here. It says, recruiting firm Worker Wonders helps companies find qualified candidates to fill vacant positions. The firm's website states that the probability that they find a qualified candidate in 3 days or fewer is 0.80. Which of the following provides the best explanation for how Worker Wonders could have estimated this probability? Okay, so which of the following provides the best explanation for how they could have estimated the probability? It says A, if all the companies Worker Wonders has helped in the past, it was able to find a qualified candidate in 3 days or fewer for 80% of their vacant positions. The average success rate of finding a candidate in this time frame for all recruitment firms nationally is 80%. So here is saying so the first option is saying of all the companies that they worked with in the past, and this one says for all recruitment firms nationally. This one's for all recruitment firms in the state. Okay. By estimating that there's a 20% chance that the firm's database will crash, making them unable to find a candidate in 3 days or fewer. Definitely not. So the best one answer is A. It's because A is talking about all the companies that they worked with in the past. So that means you're taking all of the companies that they recruited or worked with, and they found out that it was 80% that found the qualified candidate. B is talking about all recruitment firms, and it's talking about it nationally, which is not what we're talking about here with the probability with this question. And then the part C is talking about all recruitment firms in the state. So we're not talking about that. So we're just talking about the companies that Worker Wonders has worked with in the past. 80% of the time of those people they were able to find a qualified candidate. All right, so number 2, which of the following events is least likely to occur? So we're going to just kind of compare the answer choices here. It says rolling a 6 on exactly 5 out of 10 rolls on a fair 6-sided die, rolling a 6 on exactly 50 out of 100 rolls, rolling an even number on exactly 5 out of 10 rolls, rolling an even number exactly 50 out of 100 rolls, or rolling a number less than 5. So let's start eliminating answer choices here. Rolling a number less than 5 is quite likely to occur because you would have 4, 3, 2, 1. So you would have more numbers on the die that are likely to be chosen, right? So I would probably eliminate this choice compared to the other ones. Rolling an even number is better. It is more likely to happen than rolling a 6, right? Because rolling an even number would be 2, 4, and 6, which is going to be more likely than just rolling a 6. So I would eliminate the evens. And so you're just left with rolling a 6. 2 different options for that. So which one's more likely? Rolling a 6 5 times out of 10 or rolling a 6 50 times? Well, I would say it's more likely to roll. Yeah, and so I would say it's more likely to roll a 6 5 times as opposed to rolling a 6 50 times, right? Exactly 50. So because you'd have to have more occurrences of that. So it's more likely to roll a 6 5 times versus 50 times. So I would say that this is the best answer choice. All right, so in a certain town, 20% of the citizens get their daily recommended servings of fruits and vegetables. You're to design a simulation to estimate the probability that none of the 6 randomly selected citizens gets the daily recommended servings. Which of the following would be an appropriate way to assign the digits 0 through 9 to represent a citizen's behavior in the simulation? All right, so we got 20%, and so if you're doing 0 through 9, you would have to use 2 out of 10 of those numbers, right? 2 out of 10 of those numbers would have to be assigned to the citizens that get the recommended fruits. Okay, so let's see which answer choice reflects that the best. Assign 0, 1, 2 to get the daily recommended servings, and then the rest of the numbers to not get it. Well, then this is going to be 30%, right? Because that's 3 numbers out of 10. Because you have 0 through 9, that's 10 numbers. So it can't be that, right? Because that would be 30%. This one assigns 0, 1, 2, 3, 4. That would be 50%. So no. So it can't be that one either. Assign 0, that would just be 10%. Assign 0, 1 to get the daily recommended servings of fruits and vegetables. Yes, that's correct. That's 20% right there. and that's exactly what we wanted. All right, the U.S. Bureau of Labor Statistics found 34% of patient or employees who do part or all of their work at home. In a large corporation, a random sample of 20 employees revealed that 10 employees do part or all of their work at home. To determine if this is convincing evidence that the true percent of employees working from home is greater than 34%, a simulation was performed. Okay, so they did a simulation that says a dot plot shows the results of 50 trials, simulated trials of taking a simple random sample of size 20 and counting the number of employees who work from home, under the assumption that the true percent doing part or all of the work is 34%. Based on the results of the simulation, which of the following statements is an appropriate conclusion? Okay, so let's look at the dot plot here. They have the number of people, so each dot represents 50 trials, where they take 20 people, and they count how many work from home. So in this case, 3 out of 20, and for this dot, work from home. So let's convert these to percent. So 3 out of 20 is 15%. Okay, so this is 15%. This represents 20% of people work from home, 25%, 30, and so on and so forth. So let's do that first so we understand what the numbers mean. Okay. All right, so now it says, so now we're going to see, okay, based on the results, which of the following is an appropriate conclusion? So remember that for evidence to be significant or convincing, you would have, the cutoff is 5%. Okay, so it had to be less than 5% for something to be convincing. Okay, for you to have some evidence, you would have to have a close to that number, right? Close to 5%. Maybe it might be 10% or something like that. But for it to be convincing or whatever, it would have to be less than that cutoff. Okay, statistically significant. All right, there is some evidence that the true percent of employees at this corporation who do part or all of the work at home is less than 34%. Okay, so there's some evidence that the true percent who do part or all of their work. Okay, so let's look at the less than 34%. So 34%, this is the 34% here, less than 35. And so we would have to add these guys here. So adding those guys here, that's 23 of them. And here, there's 27 of them here, okay? But we only need the one on the left for part A. So there's 23 out of 50 dots, right, that are less than 34%. So 23 out of 50. Well, that's greater than 5%, way greater than 5%. So that means there probably isn't evidence. I mean, I would say there is evidence because there's way more people that are greater than 35, way more dots that are greater than 35% than dots that are less than 34%. So I probably wouldn't choose that. There's convincing evidence that the true percent of employees at this corporation who do part or all of the work at home is greater than 34%. There's convincing evidence that the true percent this was talking about is greater than. Well, if it's greater than, that'd be 27 out of 50, right? Which again is much greater than 5%. So I wouldn't say that there's convincing evidence because it would have to be less than 5% for it to be convincing. There is convincing evidence that the true percent of employees at this corporation who do part or all the work is less than 34%. Again, it's not convincing because it's not less than 5%. Oops, I circled this. I didn't mean to circle that. Sorry about that. I'm going to cross it out. D, there is not convincing evidence that the true percent of employees at the corporation who do part or all the work is greater than 34%. Yes, I would say there's not convincing evidence because it's not less than 5. So this I would agree with. There's undeniable proof that those who did true percent of employees who do part or all the work is greater than 34%. No, I wouldn't say that. All right, so number 5. So in a New York Times article, an analyst stated that the probability of a legal dispute ending in a settlement rather than going to trial is around 0.90. Interpret this probability. All right, so when we interpret probabilities, we have to interpret it in terms of long run, right? The law of large numbers. Probability is always predictable in the long run, but not in the short run. Okay, so here we're going to say when we're considering many legal disputes. Okay, so many, so large sample, we continue doing this, right? Law of large numbers. It would approach about 90% of, right, that value, right? So about 90% of them end in a settlement. Okay, so that's number 5. All right, number 6, Paul flipped the pair of coins 10 times. How many of the coin flips would you expect to land on tails? Is this result guaranteed? So we would expect, because it's 1/2 probability of getting heads, right? We would expect that 1/2 times 10 would be 5 times. We would expect 5 tails. But it's not guaranteed, right? So we say not guaranteed. And the reason is because it's due to chance, and so results are going to vary, right? Its outcomes vary due to chance, and we know that probability is not guaranteed in the short run, right? So probability not guaranteed in the short run. Okay, so So Paul recorded an H if the coin landed on heads, and a tail if the coin landed a T if the coin landed on tails. His results are shown. What proportion of Paul's flips resulted in a tail? So we count the number of tails. There's 7 tails here. So it would be 7 out of 10 coin flips times 100 would be 70%. Okay. I'll get rid of this part here. Just put equals. So 70% or 0.70, right? In fact, I'll just write it as 0.70. Sorry about that. 0.70 or 70%. And no, this is not surprising. Why wouldn't it be surprising that it's not 50%? Well, because short run behavior is unpredictable, and we've only done 10 coin flips, right? Coin tosses. So not surprising because short run behavior is not predictable. So results will vary. Okay. And C, how do you think that the proportion of tails would change if you flip the coin 200 times? Well, now if you flip the coin 200 times, we're getting more and more results, right? So if you follow the large numbers, then the proportion of tails would get closer to 0.50, right? That's what we would expect. So would approach 0.50 after many trials. As it would approach the true probability in the long run. Okay. Carly's teacher gives each student a playing card at the beginning of class to determine what table they will sit at for the day. All students with a 3 sit at one table, all students with a queen sit at one table, etc., etc. Carly ended up at a table with her best friend on Monday and Tuesday. On Wednesday, she thinks there's no way she'll be at the same table as her friend again. Explain why her thinking is flawed. Okay. Now remember that randomness is random. So it's possible that she could sit 3-4 times in 3-4 days in a row next to her best friend. But we know that it's not predictable in the short run, but it is predictable in the long run. So while it might be uncommon to see this happen in the long run, like a long streak in the long run, in the short run, it's perfectly possible for that to happen, right? So remember, probability is only predictable in the long run. But short-term behavior is unpredictable. Okay, so Carly has the same probability of sitting with her friend on Wednesday. As any other thing. Okay, in the short run, streaks can happen due to unpredictability. Okay. All right, so number 8, Francine's favorite Spotify playlist has 35 songs in it, which are sorted by date added. She listens to the playlist on shuffle mode. At one point, Francine noticed that the songs 7, 8, and 9 on the playlist played back to back. She's convinced that the shuffle mode isn't actually random. And do you agree? Again, remember, so we were talking about, we disagree with that notion because just because 7, 8, and 9 play back to back doesn't mean it's not actually random. You can have streaks, like we said. Short-term behavior is not predictable, so it's possible to have that streak, to have that, in a truly random process, patterns and streaks do occur by chance, okay? Okay. All right. So number 9, about 50% of the time, Marissa packs a sandwich for her lunch. About 25% of the time, Marissa packs leftovers, and about 25% of the time, she doesn't pack a lunch and orders takeout instead. Explain how you can use a standard 52 card deck of cards to simulate what Marissa eats for lunch on any given day. Okay, so there's different ways that you can say this, right? We just want, however way you use it, the cards, right? You have to specify that a certain cards are going to be used to represent packing a sandwich for lunch. Certain cards are going to be used for she packs leftovers, and certain cards are going to be used for ordering takeout. Now there's 4 suits in a deck, so you can take any suit, and that would be 1/4 of the deck. So if I chose diamonds, that would be 1/4 of the deck. If I chose clubs, that would be 1/4 of the deck. Okay. And there's 2 colors on a deck, right? Red and black. So you can take really any color, and that would represent, for example, packing a sandwich. So these are things that we can do. Okay, so let's just do that. Let's just do the red cards. For if you select the red card, that means she packs a sandwich for lunch, right? And then so that means we'll have to, for about 25% of the time, she packs leftovers. So let's just say, okay, well, if she gets a a heart card, that means she would pack leftovers, because remember there's 1/4 of the deck are hearts, 1/4 are clubs, 1/4 are diamonds, 1/4 etc., right? And then we'll say that if she gets diamonds, that she does not pack a lunch and orders takeout. Okay, so that's what we're gonna um, do. Oh, I'm sorry. It can't be heart or diamonds because those are both red cards. So it would have to be black cards. So because we already have chosen red for that, so that means the black cards have to be for the other ones. So in a deck, clubs are black cards and spades are black cards. So let's just do that instead. Okay. All right. So. And if you need help with decks, your standard deck, just look up a standard deck of 52 cards, and that way you can use that to help. All right, so we're going to say assign all red cards to Marissa picking a sandwich. Or packing a sandwich, I'm sorry, not picking, packing. Assign all clubs to packing leftovers. And assign all spades to ordering takeout. Shuffle the deck. And randomly select a card and record its color. Record the color selected. Or record the card, right? I guess you could say record. Because remember, we're trying to figure out to simulate what she eats for lunch on a given day. Okay, so and record the card selected. Okay, so that's it for that one. So number 10, Nick tells his sister Penny that he gets up when his alarm clock rings the first time without pressing snooze, about 85% of the time. Within the next month, Penny takes a random sample of 7 days and finds that on 4 of the days, Nick gets up when his alarm clock rings the first time, but on the other 3 days, he continues to sleep after his alarm clock rings. Does Penny have some evidence that Nick is lying? Explain. Okay, well, 4 out of 7 is basically 57%. If you were to do 4 out of 7, so it's about 57%. So, and she says that on 4 out of 7 days, he gets up the first time, right? So, but that's not equal to 85%. This is not equal to 85%. He said that on 85% he gets up the first time, right? He gets up when it rings the first time. So she has some evidence. So we would say yes, she has some evidence. Based on her sample, her sample of days, of 7 days. Since 4 out of 7 is 57%, it is not equal to 85%. Okay? And in fact, it's lower than what he claimed. Does Penny have proof that Nick is lying? Well, it's possible that this 57% occurred by chance, right? The fact that there's that this happened, it's possible that it occurred by chance. And so what we need to do is run this many times and look at the overall behavior, the long run behavior, to see if it's actually 85% or not. So we need a bunch of data, and we need to be able to plot the data and look at it as a whole in the long run, right? So no, she does not have proof. Since results vary by sample, and it's possible that his rate is 85%, but this one sample was 57% by chance. Okay. All right, so that's the difference between having some evidence versus having significant evidence, right, or having proof. All right, so Fran uses a simulation to estimate the probability that the sum of the values on 3 dice is 15 or higher. She rolls 3 dice 30 times and records a sum each time. Dot plots of result are shown. What does the single dot above the 5 represent? Okay, well, according to the description, she says she rolls 3 dice, right? And then she records a sum. So if you got a 5, that means you got a sum of 5, right? When she rolled the die 3 times, or she rolled 3 dice 30 times, and the sum was 5, right? So in this trial, she rolled 3 dice 30 times and got a sum of 5. So in one trial, I guess you could say, okay, she rolled 3 dice, but 30 times and got a sum of 5. So it only happened one time for her. Based on Fran's simulation, what is the probability that the sum of the values on 3 dice is 15 or greater? So 15 or greater, that's 2, and that's 2 out of, how many dots are there here? Okay, so yeah, it's 2 out of 30. Yeah, so she does it 30 times. Okay, I want to correct this here. Sorry about that. So there's 30 there's 30 dots here. So I should really say in one trial she rolled 30 dice, or 3 dice, not 30 times. One trial, not one time, not 30 times. Sorry. She rolled 3 dice and got a sum of 5. Okay, sorry about that. I wanted to fix that because we got 30 dots on the dot plot, and that means that she rolled the dice 30 times, but only in one trial she got a sum of 5. Okay, sorry about that. So we fixed that. So now going back to this one's 2 out of 30. Okay, so 2 out of 30. So 2 out of 30, that's about 6.7%. So it says based on the frame, what's the probability that some, so yeah, so we just put it here. So 2 out of 30 is 6.7%. So that's the probability that the sum is 15 or higher. The true probability of getting a sum of 15 or greater with 3 dice is 0.0926. Compare Fran's simulated probability and the true probability. What might account for the difference? Okay, well, her probability point, which is 0.067 compared to that, is less than, right? But we know that in the short run, it's going to be less than, greater than, whatever, right? And she did this 30 times, which is really not that much. But if she did this in the long run, we would expect that it would approach that, right? So her probability is less than the true probability, which is expected based on short run behavior. Okay, after many simulations, it would get closer to the true value. Okay, all right, so that's number 11. Number 12, a student brings a penny to class that she claims is a fair coin. To try to prove it, she tosses the coin 7 times and gets heads on all 7 tosses. For a fair coin, the probability of getting this result purely by chance is about 0.8%. So is that result statistically significant? Well, she got 0.8%, which is less than the 5%, right? So we would say yes, since the result is less than 5% and is unlikely to happen and is unlikely to happen with a fair coin. Okay, so again, based on what they're telling us here, if it's really 0.8% chance, well then it's less than 55. There's less than 5%, and so it's unlikely to happen, right? With a fair coin, that's 5% is our cutoff. If this result were 6% by chance, then okay, it could have happened by chance, right? So maybe if she got 6 tosses in a row and that would have been over the cutoff of 5%, then it was probably like likely to happen by chance. But 0.8% is really so low. What conclusion should be made? Well, then there's convincing evidence, right, at this point, because it's statistically significant. So there's convincing evidence that the coin is not a fair coin. All right, number 13. A cafe advertises a promotion during a certain week. They claim that during a promotion week, 20% of the members in their loyalty program will be emailed a coupon for a free cookie. A group of 12 friends are all members of this cafe's loyalty program. During the week of this promotion, only one of the 12 friends received an email with the coupon. If the cafe's claim is true, how many of the friends would you expect to receive the coupon? Okay, so they said 20%, and there was 12 friends, right? So that means we would expect that it would be 20% times 12. We would expect 2.4, right? Would be the average of the number of friends that would have received it, right? Okay, so 2.4. Now, is there some evidence that the claim is true? Well, it says here during the week of the promotion, only one of the 12 friends received the email with the coupon, and it says that the claim is that it was supposed to be 20%, right? And so, it appears that there's some evidence that what they said was actually not true, right? So we're going to say yes. There's some evidence that what their claim is false. Yeah. So because it was only one person that received it, right? And we know that 1 is less than 2.4, right? Which we would expect for there to be 2.4. So now we're going to do a simulation to see if it's significant or convincing evidence, okay? Simulation is done to determine the probability of getting a result like this purely by chance. So it's possible that we got only one person that got the coupon by chance, just by chance. The dot plot displays the results of 50 simulated trials. Each dot represents the number of coupon recipients in a group of 12 if the probability of winning was truly 20%. How many of the 50 simulated trials included one or fewer coupon recipients? Okay. All right. So here, one or fewer, right? So one or none. So there were, 16 of them, right? Out of 50 trials. Okay. So how many? 16. All right. So we got that for part C. Now, assuming that their claim is true, what is the approximate probability of getting one or fewer participants? Well, that's going to be 16 out of 50. There's 50 dots here on the simulation, which is 32%, which is greater than 5%. So that means it's likely that that would have happened by chance. Okay, so there's not convincing evidence that they're lying here. Okay, so no. Assuming the 20% is true, the probability of getting 0 or 1 coupons I'm just going to put in parentheses, in a group of 12 friends, by chance is 32%, which is not statistically significant. Because it's greater than 5%. Therefore, it's plausible that the claim was true. The claim is true and result happened by chance. Okay, so not enough evidence. And not significant evidence, rather. Okay, so, all right, so 14. Arav read an article on his school's website that claimed that 50% of the students at the school do not eat breakfast. Assuming the claim from the article is true, explain how Arav could simulate surveying 42 students about their breakfast habits. Well, it's 50%. You think of a coin, right? So there's different ways to do this. I mean, you can randomly generate two numbers, 0 and 1. And if it's 0, they don't eat breakfast. If it's 1, they eat breakfast, right? You could do a coin toss. If it's, if he tosses the coin and gets heads, then that means that they eat breakfast. Tails, that they don't eat breakfast, or whatever, however you want to do it. So, we're going to do the coin toss. He could toss a coin 42 times for 42 students. And assign heads as eating breakfast, and tails as not eating breakfast. Then record the number of tails. Okay. Then record the number of tails. Right here. Record the number of tails because we want to see how many don't eat breakfast, right? Okay, so when Arav actually surveyed 42 students at his school, he found that only 12 of them did not eat breakfast. Explain how Arav can design a simulation to determine if his result is likely to have happened purely by chance, or if there is convincing evidence that the article on the school's website is wrong. Okay, so he'd have to repeat this simulation a bunch of times, right? record the number of times it landed on tails, then count how many of those runs or those trials he got 12 or less heads, and then get so that he can get the percent, right? And if that percent is less than 5%, then that means he has convincing evidence, right? Okay, so conduct simulation many times, recording the number of tails in 42 coin tosses each time. Count the number of times he got 12 or fewer tails. And divide by total number of trials. To get an estimate. This estimate has to be less than 0.05 to have convincing evidence. That the article on school's website is wrong. Okay. All right, so there's that, number 14. All right, so let's look at lesson 5.2 now. All right, so it says you roll 2 fair 6-sided dice, one of which is red and the other which is green. What is the probability that the number on the red die is strictly less than the number on the green die? Okay, so remember that the probability has to be the number of times that the red die is strictly less than the green out of the total number of outcomes in the sample space. Okay, there are 36 outcomes in the sample space here, right? Because you can have, let's say this is the red die, and then you have the green die. So 1, 2, 3, 4, 5, 6, and then the green die could be 1, 2, 3, 4, 5, 6, and so you can see that there's 36 possibilities here, right? Because you could have a 1, 1, 1, 2, 1, 3, 1, 4, all 6 by 6. So we know that the probability is out of 36. And we want the number to be strictly less than the number on the green die. So that means, let's list out those outcomes. Well, you can have, for example, 1, 2, where the red is strictly less than the green. I'm going to just, actually what I'm going to do is, so 1, 2, you can have 1, 3, so on and so forth. How many are there? I'm just going to check them. This one right here, this satisfies that criteria where red is less than green. So 2 is less than 3. This would satisfy that criteria. 3 is less than 4, 5, and 6. 4 is less than 5 and 6, right? 5 is less than 6, and then if you roll a 6, then there's no way to get strictly less than green. So how many outcomes is that? 1, 2, 3, 4, 5 here. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 outcomes. So that's 15 out of 36. And then we divide this result. We reduce it, so let's divide by 3. And that gives us 5 out of 12. Okay, so the answer is B. All right, number 16. A bag of chocolates has 20 milk chocolate squares and 10 dark chocolate squares. You're given the option of blindly selecting 1, 2, 3, 4, or 5 chocolates from the bag. You win a prize if there are more dark chocolate squares than milk chocolate squares. To maximize the chance of winning, how many chocolates should you select? Okay, well, if we were to choose one chocolate, what's the probability that we would have more dark chocolate squares, meaning that we would just select one dark chocolate square. If you only choose one chocolate, then it has to be a dark chocolate square in order for you to win. And so the probability of that, well, it's just 10 out of 30 because there's 30 chocolate squares and 10 of them are dark. So this is 1/3, right? Now for part B, what's the probability of if you select two chocolates, that you would have 2 chocolate squares. Now it had to be 2 chocolate squares because it can't be 1 chocolate square, because if you have 1 chocolate square, 1 milk chocolate square, then you don't win a prize. So we're talking about the probability to win the prize, right? So it had to be 2 dark chocolate squares. So what's the probability of getting 2 dark chocolate squares? Well, it's going to be, if you select the first one, then that would be 10 out of 30. Right, the same as A, but that's only for one of them. So you would have to it'd have to be dark chocolate and dark chocolate. And remember that the probability of when you have and, that means you're multiplying the probabilities. So it's the probability of dark chocolate times the probability of dark chocolate, given that you've already selected a dark chocolate. So you'd have to multiply the two probabilities. So 10 out of 30 for the first probability. But once we select one of those chocolates, we have 9 left over out of 29. Because we've already selected one dark chocolate, so there's 9 left. And we've already selected one chocolate, so there's only 29 left in total. And so the probability is 10 out of 30 times 9 out of 29. Okay, and let's multiply that and see what we get. So 10 times 9, well, it's going to be 90 on the top. But let me just multiply it. 10 out of 30 times 9 out of 29. So that's 0.1034, which is less than 1/3, right? 1/3 is 0.33. So to maximize the chance of winning, she would have to select 1. If she tries to do 3, 4, 5, or 2, 3, 4, 5, it's just going to be less, okay? So it had to be 1 to maximize the chances to win, according to what we see here. All right. But let's look at one more probability. What's the probability that she would win if she selects 3 chocolates? Let's calculate that probability. Well, that would be the probability that she has. She can either have she can have 2 dark, 2 dark and 1 milk chocolate, or, right, she could have 3 dark. Let me just put or 3 dark. Okay, so then how do you calculate that probability? Remember, if you have or, that means you add the probabilities. If you have and, that means you multiply the probabilities. So we need the probability of 2 dark and 1 milk chocolate, or, which is plus the probability of 3 dark chocolate. 3 dark chocolate means dark and dark and dark, right? Same thing here. This is like saying dark and milk chocolate. Okay, so all right, so what's the probability of getting dark? 10 out of 30. Now, if she selects a dark, the probability of getting the next dark is, and so on and so forth. Like there's, you have to combine those. But either way, it's going to be less than 1/3 based on what we're saying. Okay. Now, it's actually more complex to calculate this than what I'm saying, because you can get a dark milk chocolate, but then you can also get a milk chocolate for the first one and then 2 darks, right? So there's actually more combinations than what it says here. And that's beyond the scope of this lesson right currently, okay? All right, so let's look at here. According to a recent report, 26% of U.S. households own a pickup truck and 8% of U.S. households own a motorcycle. Suppose that a U.S. household is selected at random. What is the probability that the selected household owns a pickup truck or a motorcycle? All right. All right. So let's do this. So according to, remember, they're talking about or. When you're talking about or and probability and statistics, you're really saying it could be either a pickup truck or a motorcycle or both. So when they say they own a pickup truck or a motorcycle, that means it could be either pickup truck or motorcycle or both. So really, the probability of, let's say T is for truck and then M is for motorcycle, you have the probability of T or M. Now the probability is the probability, you'd have to add the probabilities, the probability of truck plus the probability of motorcycle, but you'd also have to subtract what they have in common, okay? This is on the AP formula sheet. You have to subtract the probability of both, because there are households that have both, right? A pickup truck and a motorcycle. It's not just exclusively one or the other. You can have households with both, right? So you want to take that into account. So here we have the probability that they have a truck is 26%, 0.26. You have the probability of the motorcycle is 0.08%. But the problem is you don't have how many have both, right? They don't say that. And so there's no way to tell this probability. Okay, so you cannot determine this probability from the information. All right. So just be careful with that. We need to know what's the probability of both, right? All right, so number 18, a survey was sent to a random sample of individuals to learn about their traveling preferences. Of the 140 individuals who responded, 45 individuals reported United as their favorite airline. 102 said they fly only with a carry-on rather than checking a bag. Let A represent the event of an individual reporting United as their favorite airline, and B represent the event of an individual flying with only a carry-on. Which of the following statements is true? Okay, so let's, I think for this type of question, it's probably better to set up a two-way table just to kind of see what's going on. So we're going to say A means that they reported United as their favorite airline. And that means that we're saying AC is individual did not report that as their favorite airline. And then we have B means they fly only with a carry-on, and not B means that they do not fly with only a carry-on. Okay, so let's just kind of do this here, and let's do our totals as well, just to get an idea of what's going on. So we know that the total for those that want United as their favorite airline, or they reported United as their favorite airline, is 45. So that's the total for that row for A. And remember that there are 140 individuals total, according to what's says there. And that means that 95 of them do not report United as their airline. Okay. We also know that 102 fly only with a carry-on, so that's the total for B. And that means for it to be to add up to 140, this would have to be 38 that do not fly with a carry-on, with only a carry-on. And that's really all the information we have. We don't have any specific information about A and B or anything like that. So let's see which question we can answer. Now it says, for the first part is the probability of A or B is equal to the probability of A plus the probability of B. And remember, that's incorrect in this example. Well, that's incorrect in general, but this would be correct only if there is if the events are mutually exclusive. Mutually exclusive means that they cannot occur at the same time. But here you could have someone report that they like the airline and also at the same time only fly with a carry-on. So remember that there should be an extra probability here. It should say probability of A and B, and therefore this cannot be correct, okay? We would have to take into account the probability that they have both, okay? So that's why A is wrong. B, the probability of A and B is greater than the probability of A or B. Well, we can't really say too much about that because we don't actually know the amount of people that are A and B. right? So really, we can't really tell too much, give too much information about that. Although it's very unlikely that that's true, because A or B combines A plus B, and so that's likely to be greater. Even though you have to subtract this, it's likely that it would be greater than not. But we can't really say too much about B without knowing what this is. All right, so we'll skip that and do one that we can answer. The probability of A is greater than the probability of not B, BC. Okay, so B complement there. Well, let's see if that's true. Well, the probability of A is 45 out of 140. The probability of BC is 38 out of 140. So it looks like probability of A is greater than that. So we're going to select that as an answer. Let's look at the other choices. Probability of A complement is equal to probability of B. Now, the probability of A complement is 95 out of 140, which is not equal to the probability of B, which is 102 out of 140. So that can't be right. And then E, it says probability of A or B is greater than the probability of A plus probability of B, and that's incorrect because remember, you would have to include the minus probability of A, or no, I'm sorry. That'd be incorrect because the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. And there's no way that that's going to be greater than probability of A plus probability of B, okay? Because you're subtracting this, so you're subtracting a number on the left side, so there's no way it's going to be greater than the same number on the right side. So it's not E. The best answer is C. All right, number 19. A variety pack or box of instant oatmeal contains 30 packets of 5 different flavors of oatmeal. The number of packets for each variety is given in the table. Suppose you randomly selected a packet from a full box. What is the probability that you select a plain oatmeal? Okay, so let's use proper notation. So probability of plain. And it says you randomly select a packet from a full box. Okay, so so we have plain oatmeal. Okay, so it says we have 30 packets right there of 5 different flavors. So they have to add up to 30 in total. Okay, so let me just say the total is 30. All right, so plain. So plain is going to be 10 out of 30, right? Which is 1/3 or 0.333. Now, what's the probability that you don't select plain oatmeal? Okay, so the probability of not plain, or we can say plain, we're going to use the notation, plain complement. Now, we can use the complement rule for this, right? So we know that to not get plain, I would have to either add cinnamon, brown sugar, apple, or peach, or I can really just subtract from 1, right? From 100%. So I can take the 30 minus the 10, and that will be 20 non-plain flavors, right? So that's what I'm going to do. So minus is equal to 1 minus the probability of plain, and we just did that. We said it was 10 out of 30. That means there's 20 out of 30 non-plain flavors, which is 2/3, which is 0.667, approximately. What's the probability that you select peach flavored? So now they're asking about the unknown, but we know that the peach, we'd have to add the rest of them, right? So, well, we could subtract from 1, 1 minus the rest of them, and that will give us the peach, right? So probability of peach is 1 minus the probability of not peach, complement of peach. And so we could just add these other ones. So we got 10 plus 5 plus 8 plus 4 out of 30, which is 27 out of 30. So it's 3 out of 30, which is 1/10 or 0.1. Or yeah, 0.100. Okay, basically just add the other flavors, subtract from 30, and you get the number of peaches, and then put it out of 30. All right, what's the probability that you select either cinnamon or brown sugar flavored oatmeal? Okay, so probability of cinnamon or brown sugar. Okay, so this is, remember, the probability of cinnamon plus, remember, according to the rule, according to the general addition rule, you can add these together, right? Okay, and you can subtract what they have in common, but there's nothing that they have in common, right? They're either cinnamon or they're brown sugar. They can't be both in this case, right? In this case they can't be both because they're specifically certain flavors, right? So we can just simply add them and not have to worry about any results, any thing. So we have 5 out of 30 and then 8 out of 30, right? So 5, 30 plus 8 out of 30. So that's 13 out of 30, which is 0.433. All right, so next one, number 20. Kelly rolls 2 fair 6-sided dice and records the sum of the 2 numbers. Complete the table below showing the sample space of all possible sums you can get from rolling 2 dice. Okay, so there's 36 possibilities. Now you can have 1 and 1, that's 2, 1 plus 1. 1 plus 2 is 3, 1 plus 3 is 4, 5, 6, 7. 2 plus 1 is 3, 2 plus 2 is 4, 2 plus 3 is 5, 2 plus 4 is 6, 2 plus 5 is 7, 8, and so on and so forth. Okay, so we're just going to continue adding these up. It always goes by ones, so it's easy to just do that. All right, so there's our table. So what is the probability of getting a sum of 7? Okay, all right, so probability sum of 7. Well, how many sums of 7 are there? Well, there's 6 of them, right? So it's 6 out of 36, which is 1/6, which is 0.167. All right, what's the probability of a sum of 9 or higher? So 9 plus. Well, that's 9 or higher, so 9, 10, 11, or 12. So we have to add those together. That's a total of 4 plus 3 plus 2 plus 1. That's a total of 10 out of 36, which is 5 out of 18 if you were to reduce it, which is 0.278. Okay. What's the probability of getting a sum that's even? So probability of sum even. Okay. So even sum, so that means 2, 4, 6, 8, 10, 12. So just add those together. Okay. So that would be 18 in total, which is a half, which is 0.5. There you go. So that's how you do that. Define 2 events that have the same probability. Okay, so we want to have 2 events that have the same likelihood of happening. Let's see. Well, there's 3 4s and 3 10s, so you could they have the same probability of happening. Let's say a sum of 11 and a sum of 3. There's 2 out of 36, and then for 11, it's 2 out of 36. So let's just do that. Those have the same probability. There's multiple answers for this, by the way. You just have to select 2 that have the same probability. Getting a sum of 3 and getting a sum of 11. They have the same probability. Okay, are all outcomes in the space equally likely? Are all outcomes in the sample space equally likely? So there's a distinction. In G, it says, are all sums equally likely? Are all outcomes in the sample space equally likely versus are all sums? Okay, so yes, all outcomes are in the sample space are equally likely because each combination of rolls is equally likely, but the sums are not. The results are different for summing, right? So that's the difference between F and G. So yes, each combo of rolls is equally likely. But here is no. For example, getting a sum of 6 has more outcomes than getting a sum of 3. All right, so that's that. Okay, so 21, it says at many universities, students rate the professors at the end of the semester on a 1 to 5 scale, where 1 is awful, 5 is awesome. Probability model for the ratings of one professor is given. Okay, suppose a student who has rated this professor's class is randomly chosen. What's the probability that the student rated the professor a 3 or higher? So 3 or higher, you would add those probabilities. Okay, so I'm going to say probability. So we're going to say x is equal to the rating. And so we want x to be greater than 3 or equal to 3. So that means it could be 3 or 4 or 5, right? So we just add those probabilities. So 0.13 plus 0.35 plus 0.41. And that would give us our result. Okay, 0.89. What's the probability that the student did not give the professor a rating of 5? Right? Well, probability of not 5, right? So I'm going to say not 5 is 1 minus the probability that they did give a score of 5, right? So the probability that they did give a score of 5 is 0.41. So we could just do 1 minus that, which is 0.59. All right. Identify the 2 events that would be considered complements in this context. Show mathematically that they're complements. Okay. I don't know. Let's see. Let's do 2 opposite events. Giving a rating of 3 or lower, and giving a rating of 4 or higher, right? Those are complements because the probability of this one, so 3 or lower, 3 minus, would be 3 or 2 or 1, right? Which would be adding these numbers up together. Which would be 0.22, so it would be 0.24. And then probability of getting a 4 or higher is 0.35 plus 0.41, which is 0.80 or 76. And these are complements because they add up to 1, right? So 0.24 plus 0.76 is equal to 1. So that's how we know that they're complements, okay? Okay, so number 22, this is just an example. You have to just provide 2 examples that would be complements. All right, number 22, Brett asked his classmates in his first hour whether they had siblings and whether they had a pet. He recorded the information in the two-way table shown. Suppose a student from Brett's first hour is chosen at random. Define the following events. X has a sibling and Y has a pet. All right. Okay, so we want to find the probability that of X, which is that they have a sibling. Okay, so has a sibling. Well, we know the total is 24. So the probability of X is equal to 24 that have a sibling out of a total of 27. Okay, which let's do that as a decimal, 0.889. Okay. So 0.889. And then explain what this means in words. This is just the probability that they have that a randomly selected classmate has a sibling. Okay, so the probability that randomly selected classmate has a sibling. All right, and then it says find the probability of P of Y complement. Okay, so y complement. So that means not y. That means that they do not have a pet. Okay, so no pets. There's 12 with no pets out of 27, right? So the probability of no pets, 12 out of 27, which is 0.444. Okay. So it's the probability that randomly selected classmate has no pets is 0.44. Okay. All right. Find the probability of x or y. So the probability, x union y, or x or y, same thing, means the same thing, is equal to the probability of x plus the probability of y minus the probability of both, okay, x and y. So that's by the general addition rule. So the probability of x is 0.889, so it's 24 out of 27. The probability of y, that they have a pet, is 15 out of 27, minus the probability of both. So how many have a sibling and a pet? Well, that's 13. Okay, so 13 out of 27. So you combine those together and you get 26 out of 27, which is 0.963. Okay. And so this is the probability that randomly selected classmate, I'm just abbreviating here, has a sibling or a pet or both, okay, is 0.963. All right, so are the events x and y mutually exclusive? Explain. Well, no, they're not mutually exclusive because you can have a pet and a sibling at the same time, right? They're not, so you can't, so they're not mutually exclusive. Since you, a student or a classmate or whatever, say since an individual may have a sibling, may have both a sibling and a pet. Okay. So mutually exclusive means that there's no overlap. You can't have both events occur at the same time. But here you can, so therefore they're not mutually exclusive. So next one says, suppose that a person from the United States is randomly selected. Determine if each pair of events would be considered mutually exclusive. And explain. Okay. So is this having a bachelor's degree and not having a bachelor's degree? Well, yeah, those two events are mutually exclusive. You can only have one or the other. You can't have both a bachelor's degree and not have a bachelor's degree at the same time. That just doesn't make sense, right? So yes, since both events cannot occur at the same time. Okay, having a bachelor's degree and having a doctorate degree. Well, those are not mutually exclusive because you could have a bachelor's degree and have a doctorate degree, right? You don't just because you have a bachelor's degree doesn't mean that you don't have a doctorate degree, right? You might also have studied for a doctorate degree. Since an individual could have both a bachelor's degree and a doctorate degree. Having a bachelor's degree and having attended college. Okay, well, those are not mutually exclusive, right? Because you could, if you have a degree, there's a lot of students that have a degree and they attended college same time, right? So no, so it's not mutually exclusive. All right, having a 9 a.m. philosophy class and having a 9 a.m. statistics class. Again, those are not mutually exclusive, or well, here in this case, if they're different times, then they're not mutually exclusive. But if you have a 9 a.m. philosophy class and a 9 a.m. statistics class, well, then you got a problem, right? You can only go to one or the other, and your schedule is wrong. So then you have to fix it, right? You have a conflict, right? So if you have something like that, well, that's not possible for you to have both, right? Um, so in this case, you're going to say, no, it can't happen at the same time. It shouldn't be happening at the same time. So it is mutually exclusive, right? Since both events should not occur at the same time. Okay. Oops, just say both here. All right, number 24. In a class of 24 students, 15 students had been to Mount Rushmore, 5 students to Mount Rushmore and Yellowstone National Park, and 3 students had been to neither. Suppose a student from the class is selected at random. Make a Venn diagram to represent this scenario. Okay, so we'll say M for Mount Rushmore, or yeah, and then Y. We'll actually say R for Rushmore, and Y for Yellowstone. Okay, so we'll make a Venn diagram then. So Venn diagram has the circles and then the rectangle for the sample space. So here we're going to say this is R for Rushmore and then Y for Yellowstone. Now in a class of 24 students, 15, it says 3 students have been to neither, so that means they're over here at 3. Okay. Now it says 15 students have been to Mount Rushmore and 5 students have been to Mount Rushmore and Yellowstone Park. Okay, so 5 have been to both, so that would be over here, right? 5 have been to both. Now it says 15 students have been to Mount Rushmore, so that means this has to be 10 because there's a total of 15 students that went to Mount Rushmore. 5 of them went also to Yellowstone, so that means there's only 10 that only went to Mount Rushmore and not Yellowstone. And now we have 10 plus 5 plus 3. That's a total of 18. Now there are a total of 24 students, so we can subtract that from 18 and we have 6. That means there were 6 that only went to Yellowstone. All right, there you go. So that's our Venn diagram. So find the probability of Mount Rushmore and Yellowstone Park. Well, that's 5, right? 5 of them. So this is equal to 5 out of 24. 5 out of 24 is 0.208. Okay. We're going to start, doing the probabilities of decimals too. Find the probability of Yellowstone Park. Yellowstone Park is all of these combined because they're all part of Yellowstone, okay? They're all part of the Y circle. So we have 5 plus 6 over, so 5 plus 6 over 24, that's 11 out of 24. And then of course we're going to need that as a decimal, 0.458, okay? All right, find the probability of Mount Rushmore or Yellowstone. So Mount Rushmore or Yellowstone, that means it could be 10 here plus 5 plus 6. Either of these, Mount Rushmore or Yellowstone. So you add these three numbers. You don't care about the ones that went to neither, right? So it would be 10 plus 5 plus 6 out of 24, which should be 21 out of 24. So that's 0.875, okay? And then it says find the probability of Yellowstone and not Mount Rushmore. So that means they're in Yellowstone, but they're not complement. The C means complement. So not Mount Rushmore. So they're in Yellowstone, but not. So that's these guys. They're in Yellowstone, but they're not in Mount Rushmore. Okay, so it's 6 out of 24. Okay, yeah. Okay, so 6 out of 24, which is 1/4, which is 0.250. All right, that's going to do it for that one, guys. So number 25, there are 18 desserts at a potluck. 7 of the desserts are gluten-free and 4 of the desserts are dairy-free. The probability of randomly selecting the dessert that's either gluten-free or dairy-free is 0.5. How many desserts are gluten-free and dairy-free? Okay, so let's use the general addition rule. Okay, so we're going to say G gluten-free, D dairy-free. So, okay, so remember that. So the general addition rule, we want the probability of gluten-free or the probability that they're dairy-free. Now, they want the probability of and, but I'm going to use the or so that you can calculate the and. Remember that according to the general addition rule, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of both. So the probability of G or D is the probability of G plus the probability of D minus the probability of both, right? And this is what we're trying to look for. We know that the probability of, it says either gluten-free or dairy-free is 0.5. So this right here is 0.5 right there. Now the probability of G, let's actually calculate that. The probability of G, it says that there's 7 gluten-free, so that's 7 out of 18, right? So we're gonna use that number. And it says the probability of, so well, let's see, what's 7 out of 18 as a decimal? 0.3889. Okay, so 0.3889. Okay, so let's use that. So 0.3889. So let me just use that number. And the probability of D, dairy-free, well, there's 4 dairy-free, so it's 4 out of 18, right? So 4 out of 18, that's 0.222, okay. Okay. And then minus the probability of G and D, okay? So if you want to solve for the probability of G and D, you could just add these and then subtract that from 0.5, right? So we're going to add these together. Really, if you add them together, is 7 plus 4 is 11 out of 18, okay? So really, if you add them together, you should get 0.6111, okay? So 0.6111. And then we could subtract that from 0.5. And that will give us so 0.6111 minus 0.5, so that's just 0.111. And that's the probability. So that's the probability that they're gluten-free and dairy-free. All right, hopefully that made sense. So we're using the general addition rule to help us to find the and probability. All right, problem number 26. A group of 66 upper-level math teachers was surveyed. Each teacher was asked to give their number of years of teaching experience and whether the first period of the day was an AP class or a non-AP class, non-AP math class. Results are shown in the table. Suppose a teacher from this group is selected at random. Use appropriate notation to express and find each probability. So what is the probability that the teacher has 6 to 9 years of experience and teaches an AP math class during their first period? Okay, so the probability that the teacher has 6 to 9 years of experience and teaches an AP math class. All right. Okay, so first off, we're going to need to find the totals. Okay, so let's find the totals of here. So non-AP math class, we have to add these up. So it's 23, 26, 32. This is 3 plus 5 plus 5 plus 21, so that's 31, so it's 34. And then we're going to find the totals here as well. So this is 16, 15, 8, 27, and then the total, which should be 66. All right, so what's the probability that a teacher had 6 to 9 years of experience and teaches an AP math class? Okay. All right, so probability of 6 to 9 years and first period. And A. So we're going to say A means AP first period. Okay. All right. So yeah. So in this case, you want and. So both. So that means right here, 5 have AP math class and 6 to 9 years of experience, right? So it's 5 out of 66 folks. All right, and do that as a decimal, 0.076. We're just gonna 0.0758. I'm just gonna write them out. 0.0758. Now, what's the probability that the teacher teaches an AP math class during their first period? All right, so AP math class during their first period. So that's 34 of them. Okay, out of 66. So 34 probability of A is 34 out of 66. Let me 0.5152. Okay. What's the probability that the teacher has 3 or more years experience? Okay, so probability of 3 plus. Okay, so that means it's 3 to 5 or 6 to 9 or 10 plus years, right? So it's these guys. So that's going to be 10 plus 3 plus 6, right? So 10 plus 3. Oh, actually, it has to be just. It can't be just that. So I have to be careful with that. 3 or more years, it would have to be these numbers right here. Okay, so 3 or more years. 15 had 3 to 5 years. 8 had 6 to 9 years, and 27 had 10 plus years. So I have to add those up. Okay, so it'd be 15 plus 8 plus 27 out of 66. Okay, which is 50 out of 66. And that would be 0.7576. Okay. What's the probability that the teacher has 0 to 2 years experience or teaches a non-AP math classes? So, all right, so 0 to 2 years experience, that's this first row, or on non-AP math. So that means you have 13 and 3. That's where they have 0 to 2 years experience. So that's 16 teachers, or they teach a non-AP math class. So you can also combine these people, right? So they can either be the 13 and the 3 where they teach 0 to 2 years, or they could be the 10 plus 3 plus 6 where they don't teach an AP math class. Now we don't want to add the 13 twice, right? So we're just going to not add it twice. So 3, 13, 10, 3, and 6, okay? And we just add those together. So now another way of doing that is basically if you were to add them together, 32 plus 16, right? You would just have to subtract the 13 that you added twice. So that's another way of doing it. Okay. So that's actually the way I'm going to do it here. Okay. So the probability of 0 to 2 years of experience, 0 to 2, or non-AP math class, so not A, is equal to the probability of 0 to 2 plus the probability of not AP math class minus the probability of both 0 to 2 and not AP math class. All right, and so the probability to 0 to 2, then that's 16 of them, right, out of 66. Now the probability that they don't teach an AP math class, that's 32 of them out of 66. But notice that if I add the 16 to 32, I'm basically counting 13 twice. So I'm going to subtract the probability that I have 0 to 2 and AP math class, right? And non-AP. And that would give me the same result. Okay. That's what we have. So when we add these together, we should get 35 out of 66. Let's double check that actually. So 35, so they get 35 out of 66 here. 0.5303. And notice you get the same result if you added 13 plus 3 plus 10 plus 3 plus 6, you would still get 35 and then out of 66. Okay, all right, so let's look at 5.3. We're finishing done with 5.2. Now we're looking at 5.3. All right, so number 27. The students and teachers at a small high school were asked if they prefer vanilla or chocolate shake. Their answers are summarized in the table. Who at this school is more likely to choose vanilla as their preferred shake flavor? A student or a teacher? Justify your answer. Okay, so here they're imposing a condition, guys. They're saying, okay, who is more likely to choose vanilla? If you had a student, are they more likely to choose vanilla? Or if you had a teacher, are they more likely to choose vanilla? So this is the condition, right? The condition is they're a student or they're a teacher. And so, okay, so we need the probability, V for vanilla, and we'll say S for student and T for teacher. So the probability of vanilla, given that they're a student, so we're looking at just students, what's the probability that they would choose vanilla? Okay, so there's 536 students. Out of just those students, 288 chose vanilla, right? And then we'll compare that to the teachers. So the probability that they would choose vanilla if you're only looking at teachers. So there's only 22 teachers and 17 of them prefer vanilla. So if you were to compare these, well, I mean, 288 out of 536 is what, 50%, 53%? And so this is 0.5373. And the vanilla, I mean, that's way more than 50%, right? So it's 77%. So 0.7727. So definitely the teacher is more likely to choose vanilla, right? So probability of vanilla given teacher is greater than probability of vanilla given student. Okay. All right, 28. A card is selected at random from a standard 52 card deck. The card is looked at, then returns to the deck. So it's returns, guys. So that means that, you have 52 cards again, right? You took it and you put it back. Then you shuffle it and another card is randomly selected. What is the probability that both cards are clubs given that the first card was black? Okay, so, all right. So the probability... All right, so it says, what's the probability that we have a club and a club given that the first card was black? Okay, remember how to calculate conditional probabilities. Conditional probability to calculate is the probability of A given B is the probability of A and B divided by the probability of B. The given always goes on the bottom, okay? And then the top is both of them. So here we want the probability that we have club and club. Okay, so we got club and clubs, and the first card was a black card, right? Given that the first card was a black card. Now, clubs are black cards, so really this is the same thing as saying clubs and clubs, right? So when we say this, when the first card is a black card, that includes the club cards, right? Okay, so really this is just saying the probability of really it's the same thing as saying the probability of both of them being clubs, right? Because a black card is a club, or a club is a black card. Okay. All right, so the probability of club and club, basically, and over the probability of a black card. Okay, so here we have the probability of club and club. So to get two clubs, you'd have to do the probability of clubs times the probability of clubs, right? So let's do that here. The probability of club and club. You have to multiply the probability of getting a club, which is 1 out of 4, because there's 13 club cards out of 52, which is 1/4. Okay, times another club card, 1 out of 4. Now it's still going to be 1/4 because you're putting the card back into the deck, right? So it's still going to be 13 clubs out of 52. So it's still going to be a 1/4 chance. So 1/4 times 1/4, right? So we have 1/4 times 1/4 for the clubs and clubs. Club for the first card, club for the second card. Out of the probability of a black card, probability of black cards is, well, there's 26 black cards out of 52, which is a half, okay? So a half. So here we have 1/4 times 1/4 is 1/16 divided by a half, which is 2/16 or 1/8. Okay, so the probability is C. Okay. All right, so number 29. Suppose that two fair six-sided dice are rolled. Let A be the event that at least one of the two dice lands on a 5. Let B be the event that the sum of the two dice is 7. Which of the following is true about the events A and B? Before that, I want to also kind of explain this in another way. For number 28, maybe a way that might be more, another way of looking at it. So it says, what's the probability that if both cards are clubs, that the first card was black, right? Given that the first card was black. So probability of both clubs given first is black, right? So when we select the first card, right, we would have, let's think of it like this. So you can say, okay, the probability that the first card is clubs, given that the first card is black. What's the probability of that? Well, okay, so if it's a black card, there's 26 black cards. 13 of them are clubs and 13 of them are spades. So given that it's a black card, 26, there's a 13 out of 26 chance that it would be club, right? And then which is the same thing as a half. Okay. Now the probability that the second card is a club, right, is simply well, there's 13 clubs out of 52. We don't care about the first being black for this one because the first being black doesn't impact the second one being clubs. So it's going to be 13 out of 52, right? Which is 1/4. And so you can just multiply these together, okay? Okay, and then you multiply those together, 1/2 times 1/4. The probability of club and club, 1/2 times 1/4 is 1/8. So that's another way of looking at it, which I think it's intuitive. So either way, we have 1/8. So number 29, suppose that two fair six-sided dice are rolled. Let A be the event that at least one of the two dice lands on a 5. Let B be the event that the sum of the two dice is 7. Which of the following is true about the events A and B? Okay, and so they're asking, okay, well, are the events mutually exclusive, independent, or any combination thereof, right? Which combination? So let's talk about mutually exclusive. Mutually exclusive means that the two events cannot occur at the same time. And so if they can occur at the same time, they would not be mutually exclusive. So let's determine that. Can the two events occur at the same time? Can you have at least one of the two dice being a 5 and then having the sum being 7? Yes, right? You could have one die says 5, one die says 2. One of them, at least one of them is a 5, and the sum is 7, right? Because 5 plus 2 is 7. So you can certainly have them both at the same time. Therefore, they're not mutually exclusive. So we're going to get rid of A and B because that says that they're mutually exclusive. All right. Now, so the next thing is we want to look at independent. So independent means if two events are independent, if the occurrence of one event does not impact the probability or the occurrence of another event. Okay. So, in other words, if you have events A and B, then events A and B are independent if the probability of A given B is the same as the probability of A given not B. Okay, given not B complement. So it doesn't matter whether B occurs or not, the probability of A is still going to be unaffected. That's independent. So we have to see, okay, does the event where one of the dice lands on 5, at least one of the two dice, does that impact the probability of the sum of the two dice, or vice versa? Does the sum of the two dice being 7 impact the probability that one of them is going to land on a 5? And the answer is yes. It does impact the probability because let's look at event B. The sum of the two dice is 7. So if the sum of the two dice is 7, well, that means that there's a greater chance, or I would say there's a different chance, I guess I should say, there's a different chance that it's gonna be a 5. Okay, so let's calculate that. So what's the probability? Let's say that this is event B. Okay, so what's the probability of A given B? Okay, let's calculate that. What's the probability that the sum of the two dice is 7, given that at least one of them lands on a 5? Or I'm sorry, that at least one of the two dice is a 5, given that the sum is 7. Okay, so how many possible sums of 7 are there? Well, there's you can have 2, 5, right? You can have 5, 2. You can have 3, 4. You can have 4, 3. You can have, and those are basically the sums of 7, right? You can have 1, 6 and 6, 7, I guess, right? 1, 6 and 6, 7. So that's a possibility as well. Or 6, 1, sorry. So let's change that to 1, 6, 1. Okay. All right. So those are the possibilities: 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3, and that is it to get 7. So given that we have a sum of 7, that's 1, 2, 3, 4, 5, 6 possibilities, right? Given that, what is the likelihood or probability that at least one of them, at least one of the two dice lands on a 5? Well, this one, right? That's 2. At least one of them lands on 5, so that's 2 out of 6, or 1/3. Okay. Now, what's the probability in general? Let's just say, what's the probability that given, and actually, we can also compare this to the probability of A, right? So the probability of A should not be impacted by whether B or occurred or not. So let's actually calculate the probability of A. The probability of A is you're just getting, it says you're just getting at least one of the two dice lands on a 5. Well, how many ways do you have one of them landing on 5? Well, you can have 1, 5. You can have 5, 1. You can have 2, 5. 5, 2, right? You can have 3, 5, 5, 3, 4, 5, 5, 4, so on and so forth, right? But let's figure out what this is. So you can have 5, 5, right? You can have 6, 5, 5, 6. And that's it. So that's where at least one or more of them land on a 5. 2, 4, 6, 8, 10, 11. So this is 11. This is 11 out of 36 possibilities. There are 36 possibilities if you have two dice. because there's 6 possibilities here, 6 possibilities there, 6 times 6 is 36, okay? 11 out of 36 is not the same as 1/3, guys. Therefore, the events are actually not independent. So the answer is D, okay? Knowing whether or not the sum is 7 does change the probability that one of them lands on 5. All right, so that's that one. Number 30. For two independent events, F and G, it is known that the probability of F is equal to 0.8 and the probability of F and G is equal to 0.24. Which of the following statements is true? Okay. So let's write down the rule for P of F and G. Okay. So the P of F and G, that symbol means and. Okay. According to the general multiplication rule, you would multiply the probability of F times the probability of G given F. Okay. Now, because the two events are independent, it does not matter whether F occurs or not. Therefore, we can replace this with P of G. Because it doesn't matter whether F occurs or not, it's independent of G. Therefore, we can rewrite this as the probability of F times the probability of G, simply. Now, we know that it's equal to 0.24 according to this information. We know that P of F is 0.8, so we have 0.8 times P of G is equal to 0.24. So we're going to divide by 0.8 on both sides in order to solve for G, okay? And we get 0.30. So we know that probability of G is 0.30, so that means it can't be A or B. We also know it can't be C because it's not the probability of F given G, it's actually the probability of G given F, that's 0.30. So it can't be that. Now, what about D, the probability of F or G? Well, according to the general addition rule, the probability of F or G, you would have to do the probability of F plus the probability of G minus the probability of both. Now, we already know what probability of F is 0.8 plus the probability of G we just found is 0.3 minus the probability of both they told us is 0.24. So let's see, we get 1.1 minus 0.24, which should be 0.86. Oh, look at that. So the probability of F or G must be 0.86. And that is correct, which means that this excludes that. All right, that's number 30. All right, number 31. Sarah goes to a particular cafe every day for several months and notices that they're often out of certain items. So she starts collecting some data. She finds that when she goes to the cafe around 3 p.m., there's a 0.08 probability that it's out of regular coffee, 0.11 probability that it's out of decaf, 0.15 that it's out of tea. Suppose the drink selections are available independent of one another. On a randomly selected day around 3 p.m., what is the probability that all three drinks are available? Okay, so we want, basically, this is the probability right here. 0.08 is the probability that they're out of regular coffee, so I'm just going to put C. This is decaf, so out of D, that they're out of decaf, and then T, that they're out of tea. Okay, so we want the probability that on a randomly selected day, they would not be out of coffee, so C. They would not be out of, and they would not be out of decaf, right? So I'm going to put and that's the and symbol, that they would not be out of decaf, and the probability that they would not be out of tea. So this is the complement, C complement, D complement, T complement. Okay. Now, what's the probability that, so if there's a 0.08 probability that they're out of regular coffee, that means that there's a 0.92 probability that they're not out of regular coffee, right? 92% chance. Okay, so let me just do that off to the side. So this is equal to 1 minus 0.08, which is 0.92. Now the probability that they're not out of decaf is 1 minus 0.11, right? Which is 0.89. The probability that they're not out of tea is 1 minus 0.15, because that was 0.15 that they're out of t, is 0.85. And so by the general multiplication rule, because these are independent of each other, we can multiply them together without, just multiply the probabilities together. All right, and so we get 0.92 times 0.89 times 0.85. We figure out what this is. We can, so let's multiply these. So 0.92 times 0.89 times 0.85. So 0.696. All right, so there you go. So the answer has to be, let's write the answer here. The answer has to be D. All right, number 32. All right, it says a random sample of employed adults was surveyed regarding their work. The two-way table displays the results. Suppose an employed adult from the sample was chosen at random. Define the events X works full-time and Y works on weekends. Find the probability of X. Interpret this value in context. Okay. All right, so the probability of X, they work full-time. So how many work full-time? Well, 100 work full-time. Okay, so it's 100 out of 122, which is 0.820. So this is the probability that an employed adult works full-time. All right, now probability of Y is they work on weekends, so that's 36. So that's 36 out of 122, which is 0.295. So the probability that employed adult works weekends. All right, and then the probability of Y given X. Okay, so the probability of Y given X. So remember, the given goes on the bottom. So remember, the probability rule says that you do the probability of both divided by the probability of the given. Okay, so we'll do that. Actually, we'll do the math over here. All right, so the probability that they work both, right? That they work weekends and work full time is 28, right? That they do both, weekend and full time. So that's 28 out of 122 divided by the probability that they work full time. Well, that's 100 full-time people out of 122. So the 122s cancel, so you have 28 out of 100, which is 0.28. Okay. So it's the probability that given that an employed adult works full-time, they work weekends. Okay, so given that they work full-time, what's the probability that they work weekends? Okay, and then this one is probably a Y given. So the probability of Y given not C is the probability of Y and not C divided by the probability of the given, which is X complement. Sorry, X complement is they do not work full time. So so in this case they work part time, right? So they don't work full time according to this, right? So all right, so here there's 22 that work part time, right? So we're looking for that they work part time and they work weekends. So that let's do that here. Let's get rid of these. They work full time. They work part time and weekends. So that's 8. Okay, so it's 8 out of 20 out of 122 people over the probability that they work part time. That's 22 out of 122 people. So the 122s cancel, leaving you with 8 out of 22, which is 0.364. Another way of looking at it is given that they work part time. That's this part right here. Given that they work part time. So out of these 22 people, how many work weekends? Well, 8. So 8 out of 20, 8 out of 22. All right. Okay, so the probability that given employed adult works part-time, they work weekends. And so you notice that the probabilities here are not the same, which means that the two events are not independent. So they're asking, are they independent? Well, if they're independent, then these two probabilities would be the same. So this probability would be the same as this probability. But because they're not the same, that means that they're not independent. Okay, so not independent. The probability of working weekends changes based on whether they're employed full-time or part-time. Okay, so in this case, we're saying part-time employees tend to have a greater chance of working weekends than full-time employees, if you look at that, if you look at the numbers. All right, number 33. Pete celebrated his birthday with 20 friends. Each friend introduced themselves and how they knew Pete. He made a Venn diagram to represent the results. Given that the friend knew Pete, so that's the given, knew Pete from college, what is the probability that they work with Pete? Okay. Right. So they knew Pete from college. So given that, so we're looking at the given college, right? Given that they knew Pete from college. So we're looking at just that. So given that, that means there's 7 people. Given those 7 people, how many of those 7 people work with Pete? Well, that's 2, right? How many of them work with Pete? Well, only 2 is in the circle for work, right? So actually, let me put that as another color. 2 out of 7, okay? That's what they have. Given the red, how many of the red work with Pete? 2. So it's 2 out of 7, okay? So that's 0.286. All right, so that's how you use Venn diagrams to calculate conditionals. But remember, we can do it using the conditional formula, right? So let's do that. The probability of college, we're C for college, W for work. The probability of that they work with Pete, given that Pete knew them from college, this should be a C, not a D or a G, is the probability of W and C divided by the probability of C. Okay, so it's the probability of W and C. Well, that's 2 people that college and work out of a total of 20 friends. Out of the probability of college, well, that's 5 plus 2. College is 7 out of 20. The 20s cancel. You get the same result, 2 out of 7. Okay. All right, number 34. The probability that a randomly selected individual gets the flu in a particular year is 0.11. The probability that if a randomly selected individual is 65 years or older is 0.173. The probability that a randomly selected individual is 65 years or older and gets the flu is 0.006. Given that a randomly selected individual is 65 years or older, what is the probability that they get the flu? Okay, so let's say that if they get the flu, that's F. If they're older, that's O. And so there you go. That's what we get. So here, this is the probability right here of and both of them, okay? So we're given the probability of F is 0.11. That they get the flu. The probability that they're old is 0.173, and the probability that they get both is 0.006, okay? So we want the probability that given that they're old, so that's the given here, what's the probability that they get the flu? Okay, so probability of F given O. All right, now if we use the formula for conditional probabilities, is the probability of F and O divided by the probability of the given, which is O. And we know these numbers, so we can just plug them in. So probability of F and O is 0.006. The probability of O is 0.173. You can just simply divide those, so you get 0.035. All right. Given that a randomly selected individual gets the flu, so now given flu, what's the probability that they're old, right? 65 years or older. Well, that's the same idea as the probability of O and F, right? Or F and O, same thing, divided by the probability of the given, which is F. So O and F is the same thing as F and O. So it's still going to be 0.006. And divided by the probability of F, well, the probability of F is different. It's 0.11. So you're going to get a different result. So you get 0.055. All right. So there you go. Number 35. In Peter Lijdal's research on thinking classrooms, he observed how homework was completed when homework was graded versus when it was not graded. He also noted that students engaged with homework differently. Some completed individually, some got help, some completed by copying of others or cheating, some didn't do it at all. The two-way table gives the results from 200 students in grades 4 to 12. Suppose a student is randomly selected. Are the events completed individually and homework graded independent? Okay. All right, so let's say I is for completed individually, right? And it says homework graded. So G is the homework was graded, okay? So are those two events independent? Well, let's calculate the probability that it was completed individually given that it was graded, okay? And we're going to compare that to the probability. Let's compare that to the probability that it was completed independently given that it was not graded, and compare those two to see if they're the same. If they're the same, that means it's independent. I would think that it's not independent, because just before I calculate anything is because if the homework is graded, and they might change the probability that students do it individually. They might want to get help with it or something like that because their grade is at stake. But let's calculate it and see. All right, so the probability of independent given graded. So we're gonna combine the okay, so the probability of independent given graded is the probability of independent and graded divided by the probability of graded. Okay. So how many students got help individually or completed the homework individually and it was graded? Well, it was 24, right? So it's 24 out of a total of 200 students. It says 200 right here. And then how many, what's the probability that the homework was graded? So we need to add these numbers together. So let's add those numbers. So we got 24 plus 33. So it's 110, okay. So this is 110 right here. All right, so it's 110 out of 200. So given those 110 students, 24 completed it individually. That's 24 out of 110, and that's going to be 0.218, I think. Let's double check that. Yeah, 0.218 something. And now let's do the probability that if it's not graded, so that means it's not graded, it's 90 that were not graded. So given those 90, and really out of room here, so let me just put a little arrow here. So given those 90 were not graded, how many were completed individually? Well, 28 were completed individually.
So 28 out of 90, that's going to give you 0.311. Okay, so it looks like the two conditional probabilities are not the same. So not independent. So it looks like whether homework is graded or not does seem to affect whether they were completed individually. Okay, so not the same, so not independent. Okay, all right. Interestingly enough, are the events got help and homework graded independent? So let's do that. So help H, and then homework graded G. So again, let's do the same thing. H given G, and then probability of H given not G, right? So let's do this. Help. The total for help is 33 plus 27. That's 60. So given those people that, oh well, that's for help. Let me actually look for the graded. Given that it was graded 110, so out of the 110 people, how many got help? 33. Out of the 90 people that did not get help, how many got, how did the 90 where the homework was not graded, how many did get help? 27. So we got 27 out of 110. Okay, we can clearly compare those that are different, right? We can, out of 90, I'm sorry, not 110. Sorry about that. All right, so let's compare those numbers. So this is points 33 out of 110. So it's 0.3. Okay, so this is 0.3, and this is what is that? 27 out of 90? Oh, 0.3. So it's the same. All right, so the probabilities are the same. So events are independent. And so it appears that it doesn't matter whether the homework is graded or not. It looks like the likelihood that they'll get help is about the same. Is going to be the same, according to the data. All right, so number 36, it says a company wanted to test the effectiveness of a new digital advertisement for one of the products they sold. To do this, they looked at a random sample of 150 of their customers and sent the new ad to 50 of them. They then recorded whether each of the 150 customers made a purchase for the item in the time span of 1 week. Some of the results are given in the table below. Okay, so first off, let's just do the total. So this is 100 that didn't receive the ad, and the total for this column should be 50, right? So that's what we should know. Now it says if the ad had no effect on whether a customer purchased the item, what would you expect the counts to be in the missing 2 entries of the table? Okay, so that's an interesting question. So what would they? How would they be? How would they be? Like how? What would these numbers be? Right? Okay. So in order to do that, what we need to do is we know that if the events are independent, meaning that the ad had no effect, then that means that the probabilities should be the same regardless of whether the ad was there or not there, right? Basically. So regardless of whether they received the ad or whether they did not receive the ad, they would still have the same probability of making a purchase, right? Okay, so let's look at that. So we know that the probability that they did not receive an ad, let's just say A for ad, this is not ad. Purchase, well, actually, let's do M for make purchase. Not M for they did not make a purchase. Okay, so we're going to do the probability that they do not receive an ad. Is 100, or actually, let's do. We're going to calculate the probability. We're going to see if whether they received the ad and how that would affect their probability of making a purchase or not. Okay, so let's calculate some conditional probabilities here. So what's the probability that given that they did not receive an ad, that they made a purchase? Okay, so out of the 100 people that did not receive an ad, how many made a purchase? 24. So it's 24% chance, right, that they would make a purchase. That should be the same percent for those that made a purchase for receiving the ad. Because if it's independent, it should still be 24%, regardless of whether they made an ad or not, they received an ad or not. So let's do that. So let's do, what is 24% of 50 people? 24% of 50 people is 12. Okay, so this would have to be 12. Now let's do the probability that they did not make a purchase given that they didn't receive an ad. Well, there's 100 people that did not receive an ad, 76 made a purchase. That's 76%. So if they did not receive an ad versus whether they received an ad, it should still be 76% that do not make a purchase, right? So we're going to do 76% of 50 people, and that would give us 38. And so if it's truly independent and the ad has no effect, these are what the numbers should be, okay? And we're going to give a reason, okay? So give a reason for your answer in part A. So like, I don't know, if ad had no effect, they would behave the same way. As those who didn't receive ad. Okay, those who received the ad versus those who don't receive the ad, they will behave the same way. Okay, so that means 24% of those who made purchase is 0.24 times 50 is 12. Okay. All right, so that's how we got those numbers basically. All right, so for the board game Scrabble, there are 100 tiles placed in a bag, each containing a different letter. There are 9 tiles of the letter A. If 2 tiles are drawn randomly with replacement, so we're putting them back, what is the probability of getting a letter A followed by a letter A? Okay. Okay, so if they're being replaced, that means the events are independent. Okay. So that means it doesn't matter whether you got A the first time, it's still going to be the same chance of getting A the next time because you're putting the tile back into the pile, and so you still have the same number of A's in the pool, in the bag. So we want the probability of A and A. So that means you multiply the two probabilities, the probability of A times the probability of A. Well, there are 100 tiles in the bag, and 9 of them are A, so it's 9 out of 100. Times 9 out of 100. The probability of getting the second A is still going to be 9 out of 100 because you're putting the A back into the pile. Now, if you're not putting the A back into the pile, well, now you have 8 A's left, right? So that's going to change the probability. Okay, but here we're putting it back, so it doesn't matter. So we get 81 out of 10,000, which is 0.0081, really small chance. Now, for this scenario, are the results independent? Yes, that's what we were just talking about. So yes, whether or not A is the first tile doesn't change probability that second is an A. Okay. All right, so is an A. All right, so now part C. If 2 tiles are drawn randomly without replacement, what is the probability of getting a letter A followed by a letter A? Now you're not putting it back. So this time the probability matters. The probability of A given A is the probability of A times the probability of A given A. So now it's different. It's not the same probability anymore because there's a condition. You're not putting the tile back. So the probability of getting the first A is 9 out of 100. But now you have 9 possibilities. You chose one of the tiles. You did not put the tile back. So now you have 8 tiles left that are A. Okay, so the probability of selecting the next A is 8 out of the total. Well, how many total are there? Well, you already selected one tile and held on to it. Therefore, you have 99 left. Okay, so notice this is not independent anymore because the probability is changing. So now we multiply those together. We get 72 out of 9,900, which is 0.0073. So for the scenario in part C, are the tiles independent? No, right? Whether or not you have A as the first tile changes the probability that second tile is an A. Okay. All right, number 38. A cooler contains 27 cans of soda. 11 of the cans contain caffeinated sodas, and the rest contain non-caffeinated. All right, so 11 is caffeinated. We'll do C for caffeinated. The rest contain non, so C complement. And the rest, that means it's 16, right? Okay, Jim randomly selects 2 cans from the cooler for him and his friend. So he selects 2 cans. What is the probability that neither of the 2 drinks are caffeinated? Okay, so neither of the 2 drinks are caffeinated. So it's a probability of non-caffeinated and non-caffeinated. So probability of non-caffeinated and non-caffeinated. Okay, and this is an example of where I don't like to use the C there. I could just use C prime. So it means complement. It's the same thing. I would rather just use that rather than having the 2 C's, right? But you can do the 2 C's if you want. But I'm just going to do the prime, the apostrophe. So probably a C prime and C prime. So now this is gonna affect the probability because he's taking 2 cans. That means he's taking 1 can and then he's taking another can after that. So that's going to change the probability of the next can being caffeinated, right? Or not caffeinated. So this is actually without replacement. So without that means it's not independent. So the probability of not caffeinated times the probability that he gets another caffeinated, non-caffeinated, given that the first one was not caffeinated. Okay, so the probability of the first non-caffeinated is a 16 out of, or no, he says that neither is caffeinated. Okay, so that, yeah, neither, so it's non-caffeinated. All right, so 16 out of 27. And now the next one, now since he chose one of the non-caffeinated ones, he has one less caffeinated one, non-caffeinated one. So now he has 15 non-caffeine out of 26 because he selected one of the sodas, so he has 26 left to choose from. So 15 out of 26. Okay. Hopefully that makes sense, guys. And then you have that, so that's going to be 0.342. All right, so on January day in Michigan, the Weather Channel predicts that there's a 70% chance of snow accumulations of at least 12 inches overnight. If at least 12 inches of snow accumulates, there's a 65% chance of a snowy day on the following day. If less than 12 inches of snow accumulates, there's an 8% chance of a snow day. Make a tree diagram to model this process. Okay, so let's do the weather. So here we have greater than or equal to 12 inches of snow, which I'll say, S for snow. You can say that if you want. Less than 12 inches of snow. So this will be SC, right? Now, what's the probability of getting greater than 12 inches of snow? Well, it says 70% here, right? So if there's a 70% chance of getting that much snow, that means there's a 30% chance of not getting that much snow, right? And now, if you get more than 12 inches of snow, what's the probability that you have a snow day? Right? Snow day. So I'm just going to do D for snow day or no snow day. DC. Okay, D complement. All right, so then in this case, what's the probability that you have, if you have greater than 12 inches of snow, that it will be a snow day? Well, it says if at least 12 inches of snow accumulates, there's a 65% chance of a snow day. All right, which means that if there's 12 inches of snow or more, there's a 35% chance of not being a snow day, right? Because it has to add up to 1. Now it says in the description, if less than 12 inches happens, there's an 8% chance of a snow day. Okay, so I'm going to put snow day, or if you want, you could use D for the event. There's a 8% chance, which means that there's a 92% chance that it's a no snow day. And there's your tree diagram. And so there you go. So we'll make a tree diagram for this process. So now what we're going to do is we're going to calculate all the probabilities here. What's the probability of getting a 12 inches of snow and it being a snow day? Well, you multiply the probabilities along the way. As you travel, you multiply the probabilities along the way. Okay, so the probability of snow day and 12 inches of snow is 0.70 times 0.65, okay? Which is 0.455. Now the probability of no snow day and 12 inches of snow is 0.7 times 0.35, which is 0.245. The probability that it's less than 12 inches and it's a snow day, 0.3 times 0.08. So let me, hold on a second here. 0.024. And then the last one is 0.3 times 0.92, which is 0.276. And notice that these probabilities add up to 1. Okay. All right, so what is the probability that there is a snow day tomorrow? Okay. All right, so the probability of a snow day, let's do that. Okay, so what's the probability of a snow day? So the probability of D. Okay, well, the probability that there's a snow day is the probability that there's 12 inches of snow and there's a snow day, or there's less than 12 inches of snow and it's a snow day. So there's two possibilities, right? So we would have to add these two probabilities, 0.455 plus 0.024. Those are the two ways that you can have snow days, right? According to the tree diagram. So we add those together and that gives us 0.479. Now it says if there was a snow day, what is the probability that there is snow accumulation of at least 12 inches? Okay, so that's a conditional probability given snow day, okay? So the probability given snow day, given D, what's the probability that we have a bunch of snow, at least 12 inches? Well, the formula for conditional probability is the probability of both divided by the probability of the given, right? Now we just calculated the probability of a snow day. So that was 0.479, that's your denominator. Now the probability of snow and of at least 12 inches of snow and it's a snow day, well, that's 0.455, right? At 12 inches of snow and snow day. So it's 0.455, which is 0.950. So if there was a snow day, the probability that there were snow accumulations that were 12 inches is 95%. All right. So according to survey results from Pew Research Center, 30% of people made New Year's resolutions. New Year's resolutions. Of the 5140 people who were surveyed, 16% were in the 18 to 29 age bracket. Of the people who were surveyed, 7.9% were in the 18 to 29 age bracket. Suppose a person from the survey is randomly selected. Are the events New Year's resolution and 18 to 29 years old independent? Justify your answer. Okay, well, now we have another way to determine whether two events are independent. So because we can say, okay, the probability, let's just say R is for resolution, and 18 to 29 age bracket, we'll say A for 18 to 29 age, okay? So are the events R and A independent? Well, now we can say, okay, the probability of A and B is equal to the probability of A times the probability of B. This is only true if they're independent. So we can actually test that to see if it's independent or not. So the probability of R and A has to be the probability of R times the probability of A if it's independent. So let's find out. The probability of R and A, it says here, it says 7.9% were in the age 20 to 29 bracket and made New Year's resolutions. So that's 0.79. 0.079. Now the probability of R, meaning resolutions, is 0.30. Let's write that. Probability R is 0.30. Probability of A, they said was 16%, 0.16. So we're going to do that times 0.16. Now, this is not equal to 0.079 because if you multiply those, 0.30 times 0.16, you're going to get 0.048. See that right there, 0.048, which is not the same as 0.079. Therefore, they're not independent. That's another, so now we know another way that you can determine independence quickly if they give you the information. Is a person between the ages of 18 and 29 more likely, less likely, or equally likely to make a New Year's resolution than all survey responders? Okay, so let's calculate that. So what's the probability that given that they're 18 to 29, that they make a New Year's resolution? So remember, it's a probability of New Year's resolution and they're in the age group divided by the probability of the given, which is the age group. Now we know that in the age group, there's a 16% chance that they're in that age group. And what's the probability that they, I put Y for resolution, so it should be R for resolution. The probability that it's R and A, they told us it was 0.079. So this is 0.494. Now notice that this is greater than the probability of the resolutions, which was 0.30. Okay, so this is actually greater than the probability that somebody makes a resolution, right? According to the data, and so therefore it's greater. So it's more likely. Okay, so more likely. Okay. All right, so it says Joel often flies with United Airlines from Grand Rapids, Michigan to Los Angeles, California, which requires him to have a layover and make a connecting flight. About 22% of the flights are delayed, including connecting flights. If Joel's first flight is delayed, there's a 34% chance of his second flight is also delayed. Are the departure times for the flights independent? And how do you know? Okay. All right, so we're gonna say let's just draw. Yeah, so let's label this out. So 22% of flight. So that means the chance that his flight is delayed is 22% chance, right? So we're gonna say first flight or a given flight, right? And there's a 34% chance of the second flight. So this is for the second flight. Okay. If given that the first flight is delayed, right? Second flight given first flight delayed. Okay. All right. So are the departure times for Joel's first and second flights independent? Okay. So what we're saying is that, okay, the probability of his second flight being delayed, given that his first flight is delayed, so the probability that the second delayed, given that the first is delayed, is 0.34, which is not equal to the probability that of the first flight being hold on, let me see here. So it's not equal to the probability that any given flight is delayed, which is 0.22. Okay, so the probability of a particular delay is going to be 22% chance by itself, but it seems to be that if the first is delayed, that's going to impact the second one being delayed. And so that means that the events are not independent. That means that the first delay is actually influencing the chance of the second delay. Okay. So not independent. Okay. Okay, so then what is the probability that at least 2 of the flights are delayed? Let's do a tree diagram for this. So this one, we're going to say so this is the first flight. This one's going to be the second flight. Okay, so let me see if I can draw this as concise as I can. So for the first flight, there's a 22% chance of a delay. I'm just going to say D for delay. And then 0.78 chance that there's not a delay, so D prime. Okay, no delay. If there's 22% chance that a given flight is delayed, then that's what it is. 78% chance that it's not. And then now, given that the first flight is delayed, what is the chance of the second flight being delayed? Well, that's 34. That's what they told us, okay? So 0.34% chance that that's delayed, which means that there's a 66% chance that it's not delayed. And if given that the first flight is not delayed, what is the chance that the second flight is delayed? Well, it's still 22% chance because that's what they said. It's 22% for a given airline, right? So I guess I should call it for first flight, any flight, really. First flight, any flight. Just any isolated flight. So I should put any isolated flight, okay? So that would be delayed. And so that means that there's a 78% chance that it's not delayed, okay? All right, so what's the probability at least one of the flights is delayed? So at least one, so one or more, right? So probability that either the first flight is delayed, and well, I'm just gonna put at least one, okay? At least one delay, okay? So in order to calculate at least one delay, we need, okay, well, DD, delay, that counts. At least one delay means one or two delays. So how do we calculate the probability of delay and delay? Well, we multiply the probabilities along the way. 0.22 times 0.34. That gives us 0.0748. Now, we also want delay and not delay, right? So probability of delay and not delay, that would be at least one flight that delayed. That's 0.22 times 0.66, which is 0.1452. And then delay, not delay, and delay, that would be one of the ones that we would want too, because at least one delay, right? That would be 0.78 times 0.22, and that would be 0.1716. And then we don't care about the last one, okay? The last one is basically there are no delays, right? Which is 0.78 times 0.78. But I'm going to do it anyways, just so you can see it. So no delays, 0.78 to the second power. That's 0.6084. Now we can add these three things, and that would give us a probability of at least one delay, or we can use this number and subtract it from 1. That's what I'm going to do. I'm going to do 1 minus the probability of no delays. And you would get the same result, 1 minus 0.6084, which is 0.3916. Now, if you try adding these three numbers, you're going to get the same answer. So could we have just gone straight to that? Yes, we could have just gone straight to the no delays, calculated that probability, subtracted that from 1. Okay, but I just want to show you both ways. All right, so suppose Joel takes 3 trips from Grand Rapids to LA and back in the month of March. What is the probability? So we're taking 3 trips here, according to this. What's the probability that at least one of his 12 flights is delayed? Okay, so the probability of at least one, meaning it could be 1 or 2 or 3 or 4 or 5 or whatever, however many flights. We really don't want to do that many flights. So what we're going to do is we're going to do the opposite of that, the complement, and subtract from 1. So to get the probability of at least 1, we could do 1 minus the probability of none. The probability that there are no delays. And we already know what that is. The probability of any delay is of not delayed is 0.78. So it's going to be 1 minus 0.78. Hold on, let me make sure. It's 0.78 times 0.78. Okay. Um, 1 minus no delays, which is 0.6084 right here. Okay. 0.6084 to the 6th. Okay, and we got to be careful. How many trips is he making? Well, it's 3 trips, but how many flights is that? Well, it's 3 trips from Grand Rapids to LA and back. So that means he's doing 6 flights, right? So really, the probability that there's no delays is 0.6084 to the 6th power, right? Because there's 6 flights, okay? 6 connecting flights. So it's 1 minus that, which is 0.9493. Okay. All right. So that one's a little tricky, the last one there, but be careful with that. All right. So number 42, a nonprofit foundation is hosting a Pi Day, Pi K running race. After the event, they report 45% of runners who registered for the event to the race had never participated before. Of the runners who had participated in the race, 90% completed the Pi Day, Pi K. Of the runners who had never participated in a race before, 80% completed the Pi Day, Pi K. What percent of the runners who completed the Pi Day, Pi K had never participated in a race? Okay, it's good to just get a picture of what's going on. So let's do a little picture of what's going on. Okay. Okay. Participated before is going to be one event, and then participate or registered, I guess you could say, okay. And then we have we have participated before, and then we have those ones that completed. Or I'm just going to say Pi Day K. Okay. Pi Day Pi K. Okay. And I'm going to do, I guess I should say enrolled. Enrolled. Okay. Okay, so we have 45% of those who enrolled had never participated in a race before. Not participated before. And that means that 55% participated before. And it says of the runners who had participated before, 80% completed it. That means 20% did not complete. And it says of the runners who had never participated. Oh, I guess I got the wording different. Okay, so it says of those who had never participated in a race before, 80% completed the Pi Day challenge. So this would be 0.8, and then this will be 0.20. Completed and not complete. All right, and then it says of the ones who participated, 90% completed it. Okay, so this is the these are the numbers. Okay, it says what percent of the runners who completed the Pi Day had never participated in it before. So what is the probability that given that they did not complete the Pi Day, given that they've completed it, we're going to say C for complete, okay, that they never participated before. So we're going to do PC. PC means they never participated. So let's do that. So this will be PC, this will be P, okay? All right, and this will be C, this will be C prime, CC, C, CC. Okay, so we're just labeling the letters. All right, so what percent of the runners who completed it never participated? So we're going to do the calculation here. We're going to do the formula for this is you do the probability of both over the probability of the given. Okay, so how many people participated in both? Meaning that, or how many people did both? Meaning they did not participate and they completed. Not participated and completed. So that's 0.45 times 0.80, right? According to the tree diagram. Okay, and then over, now we want the probability of completed it. Okay, well, the probability of completed it is 0.45 times 0.80, because that's where they completed it, plus you can have participated before and completed it, right? 0.55 times 0.90. And so you can calculate that, the probability like that. And let's actually calculate that and see what we get. So it says 0.45 times 0.80, divide that by 0.45 times 0.80 plus 0.55 times 0.90. And there you go, so you get 0.4211. So which is 42.11%. All right. All right, guys, that's going to do it for the video. I hope you found this useful and informative. And as usual, I'll see you in the next one.